During this semester, in addition to Physics 354, I took Astronomy 450 that covers the topic of cosmology and its explanation with relativity. In this video, I will expand further from what we have learned in 354 on how the details of redshifts help our understanding on the properties of the universe as explained in 450. So what exactly is cosmology? Cosmology is a division of astronomy that studies the origin and evolution of the universe, from the very first particles generated in the Big Bang nucleosynthesis to the possible end of the expanding universe. Cosmology covers concepts such as string theory, dark matter and dark energy, and postulations of the multiverse. One of those cosmological measurements was the Hubble constant, discovered by measuring distances to nearby galaxies in megaparsecs, where 1 parsec is about 3.26 light years, and seeing which ones were moving away faster due to their recessional velocities. The measurements are then plotted to where the slope of the relationship equals the Hubble constant as seen in the top image. Hubble's constant current measurement is 69.8 kilometers per second per megaparsec. This gave rise to the idea of the Big Bang theory, since at one point all galaxies had to be in one place. 1 over the Hubble constant is called the Hubble age, and will always be the upper limit to the age of the universe because at some point, gravity played a factor in making close galaxies move towards us at a faster speed. Expansion slows this down. Since this is not a Doppler effect, but instead, imagine that the space between the galaxies is expanding. This is called a constant because it has to apply to any point in the universe and is not constant numerically. NASA's WMAP was a spacecraft that operated in 2001 to 2010. WMAP maps teeny fluctuations in the cosmic microwave background, as seen in the image. The patterns over huge patches of sky tell us about what was happening in the smallest of scales in the moments just after our universe was born. The cosmic microwave background shows the ancient light from the early universe and determined that ordinary atoms make up only about 4.6% of the universe, while dark matter makes up 24%. The age of the universe is approximately 13.8 billion years old, as found by 1 over the Hubble constant, but is now determined more precisely after mapping the small temperature fluctuations in a cosmic microwave background. The European Space Agency's Planck space mission ran afterwards from 2009 to 2013 and continued the study of the cosmic microwave background. In recent news, now the ESA is currently developing the Euclid mission, which should fly by the end of the decade. Euclid will study dark matter and dark energy with great precision, even greater precision than the Hubble Space Telescope has, tracing its distribution and evolution throughout the universe. Moving on from perfecting the Hubble constant, we can use this value to see if the universe is really expanding. Hubble and others made the first measurements of redshifts and blueshifts of galaxies beyond the Milky Way. They initially interpreted these redshifts and blueshifts as due to random motions, but later Hubble discovered a rough correlation between the increasing redshifts and the increasing distance of galaxies. Theorists almost immediately realized that these observations could be explained by a mechanism for producing redshifts seen in the certain cosmological solutions to Einstein's equations of general relativity. There are 3 main causes of redshifts in astronomy and cosmology. Objects move apart or close together in space, being an example of the Doppler effect. Space itself expanding, causing objects to become separated without changing their position in space. This is known as a cosmological redshift. All sufficiently distant light sources show redshift corresponding to the rate of increase in their distance from Earth from Hubble's law. Gravitational redshift, being a relativistic effect observed due to strong gravitational fields which distort space-time and exert a force on light and other particles. Hubble's law of the correlation between redshifts and distances is required by models that have a metric expansion of space. As a result, the wavelength of photons propagating through the expanding space is stretched, creating the cosmological redshift. There is a distinction between redshift in cosmological context as compared to that witnessed by nearby objects exhibit a local Doppler effect redshift. Rather than cosmological redshifts being a consequence of the relative velocities that are subject to laws of special relativity, the photons instead increase in wavelength and redshift because of a feature in space-time metric, through which they are traveling. This effect is the idea that space itself is expanding. Due to expansion increasing as distances increase, the distance between two remote galaxies can increase at more than the speed of light. But this does not imply that the galaxies move faster than the speed of light at their present location. Even though redshifts indicate that other galaxies are moving away from us, we are not at the center of the universe, because if we were to travel to a distant galaxy, it would seem that all surrounding galaxies were similarly rushing away. If you think of the universe as a balloon, and mark multiple points on the balloon, then blow it up, you would note that each point is moving away from all the others, though none are at the center. The expansion of the universe functions in much the same way as seen in the figure to the right. And that's all I got. So, yeah, that's all, folks. Great semester. See you later.